We're interested in looking at this motion of projectile motion, but in extension 1 we really simplify the motion in that we assume a few things. In other words, we're going to assume there's no air resistance, so there's no drag on it. So the only force that's acting on our particle is the force due to gravity. Everything else is negligible. In other words, force is mass times acceleration, so in the horizontal direction, acceleration will be a 0 as far as we're concerned, and in the vertical direction it's only going to be gravity, and that acts in the negative direction it's going down. So some initial conditions then. So when t equals 0, we're going to project something. For convenience, I'm going to set the origin as the starting point. Now, you might not always do that, because sometimes you might be projecting, say, from the top of a tower or a cliff or something like that. It might be more useful to set it at whatever the height of the object is. But let's, for this, just say we're at the origin. So we're going off at some angle and with some velocity. There it is. But I want to break that into the component. So horizontally, just a little bit of trig, I know it's going to be v cos theta. Vertically it'll be y sine theta. But then our particle's going to move. And so at some other point here, it's now going off. Gravity will take effect, and it's going off at a different angle now. And then it would keep going. At some point it's going to reach the top. And so all that's really happening now is it has horizontal velocity but no vertical. Because before it comes down, it has to, if you're just looking at it vertically, it has to stop to come back down, so it's at the peak. It then starts coming back down. Again, our vectors would change and down. And if we were to plot the curve in, we get a parabola. I say I've set the initial conditions at x equals 0, y equals 0, but it is whatever the problem is, we'll set it to that. Just something to note, in this sort of problem where we're neglecting any air resistance, the maximum range will always happen when theta is 45 degrees. That's all to do with the symmetry of the parabola. Let's create some equations we can work with. The only thing we know at this stage are our acceleration equations, and in the horizontal direction that is 0. A lot of times for convenience we'll say take gravity to be 10, it's a nice round number. Sometimes we just leave it as g. And then of course you could have it as 9.8. Of course it could be 10, no one says we're on Earth, we could be on some other planet where the gravity is 10, could happen. Let's work some velocity out. Separate my variables. This one's interesting because when I go to dt on the other side, of course 0 times dt is still 0, and we just end up with x equals v cos theta. Well, that's because horizontally there are no forces. So it's just travelling with constant velocity horizontally. Over in the vertical, of course, something different happens. And we have, there's the initial one, v sine theta, but gravity has some effect on it. So as time goes on, we have 10t, or the g times t is taking effect on it. There's my velocity vector, but you'll notice when I wrote this one, I didn't write v cos theta. I wrote it as magnitude of v, because we're now talking about a vector v. We don't want confusion. If I just go v, hang on, vector, number, what is it? It's probably a trivial point, but that's why I've got magnitude of v there rather than just writing v. All right, let's find displacements. Integrate that one, we get vt cos theta. Vertically, we end up with vt sine theta minus 5t squared for this one. A more general one would have minus a half gt squared. And there's my displacement. Now, I should be able to solve any problem now with those equations. Some of the common things we ask and like to find is like, well, when does it then hit the ground? You've got to think horizontally, vertically, what's happening. So when it hits the ground, what's the thing we know for sure? Well, we know y equals 0. Okay, that's what we'll solve, and we can find when it hits the ground. What's the range? How far did it go? So I want to know the range of our particle. Well, once I know when it hits the ground, then I can sub that back into the horizontal component and I'll find where it hits the ground. Greatest height. So you think, well, what happens at the greatest height? Well, the greatest height is when it stops and comes back down. So I'll solve when the vertical velocity is equal to 0. Once I know that time, I can substitute it into the vertical displacement, and that'll tell me where it happened. Angle does it make when it hits the ground? Now, of course, if I have projected from the origin under this simple model, because there's no air resistance and the symmetry of the parabola, I know that whatever I project it with, that's got to be the angle that's going to land as well, because of symmetry. But if I'm not projecting from the ground, or maybe it's actually some other point in time, and not when it hits the ground, maybe it hits some other object in the air or something like that, essentially I've got to use the velocity component. So for this one, when it hits the ground, I'll say, well, alright, when does y equals 0? But I'll substitute it into the velocity components. Well, actually, in reality, I only need to substitute it into the vertical velocity, because horizontal velocity is constant. It's always going to be that. There's my triangle. I can work out the angle. So, summary, what do we know? All we really know about projectile motion is those two simple things. Horizontally, the acceleration is 0. Vertically, it's minus g, whatever g has been defined to be. I know initial conditions. It'll be v cos theta, v sin theta, and that's pretty much it. From there, I can go and solve anything. Here's a simple little problem. I'm going to throw a ball, initial velocity 25 meters per second. To make life easy, that angle happens to be the inverse tan of 3/4. Makes the numbers nice. Determine the greatest height. Okay. Well, I need my equations. So I guess the first thing I would do is go and derive the equations. Now, a lot of times in the HSC, they'll give you some to save you time. And they'll say, oh, here's the displacement equation. You don't need to derive these. But if they don't, you've got to derive them. I'll work out my initial conditions. There's my triangle. It's good old 3, 4, 5. So v cos theta becomes 20. V sin theta becomes 15. So I know what's happening initially. Okay, start with these. For convenience, I'm using 10 for gravity. And horizontally 20, no surprises there. We know it's going at a constant value. And y, we get 15 minus 10t. Displacement, integrate each component. There it is, 20t horizontally, 15t minus 5t squared. Okay, I've got all the equations I should need to go and solve any problem. So greatest height was what we were trying to find. That happens when y dot equals 0. That's t equals 3 on 2, it turns out to be. Okay, sub it in, 45 on 4. So 11¼ meters above the ground. That's its greatest height. What's its range? So these were the common sort of questions. Okay, now here I can get the time of flight straight away because of the symmetry of our problem. We just found it takes 1.5 seconds to get to the greatest height. Therefore, it must take 1.5 seconds to come back down again. So I could just say, oh, well, I now know time of flight is 3 seconds. So sub it in, I've got the range. After half a second, what's the velocity and direction? Well, I know it takes 1.5 to get to the greatest height, so I know at least it's going up after half a second. I know that. I can work out the vertical velocity, and that confirms it's going up because it's a positive value. Draw a triangle. We can now calculate the velocity and direction. In fact, I've already worked out the velocity by Pythagoras there. The angle, 2634. There we go. So after half a second, it's travelling at 10 root 5. Angle of 26 degrees 34. Let's now start looking at more interesting problems that we come across with the extension 1. So that one I just did before, they're the sort of basic projectile motion questions. Let's have a look at the last few that we've seen. So 2022. Video game designer has got this game. He wants to include an obstacle in the game. Player reached one side of a pit. Going to shoot a projectile to hit a target on the other side of the pit. And if it hits it, I guess some bridge opens up and it can cross the pit or something like that's going to happen. However, the instant they shoot, the target starts moving. Okay. But we know it's going to be at a constant speed, and that's half the initial speed of the projectile, as shown in the diagram. The initial distance between the player and the target is d. Projecting angle of theta, speed is 2u, and so on. The only thing we can adjust in this problem is the angle. So in that game, the only thing they can play with is the angle they're going to project at. Everything else is fixed. They gave us the displacement vectors of the two things, so it saves us deriving these ones. The top one there is for the projectile, the bottom one is for the target. And they've written it in column form for us. And this is what we had to do. Show that for the player to have a chance of hitting the target, d, must be less than 37% of the maximum possible range. So it wasn't scaffolded, it was simply, righto, go and do it. It would have been one of those ones that are worth maybe 4 marks, 3-4 marks. Pull it all together. Well, if it's going to hit the target, I've got to know where my projectile hits the ground, I guess. So when it hits the ground, I still don't know what it is horizontally, but at least I know vertically the component would have to be 0. It's hitting the ground. Now that means, remember, there's the horizontal component there, 2ut sine theta minus g on 2t squared. We can at least now find the time, or an expression for it anyway. It's either going to be 0, well, that's when I'm launching it. Of course it's at the ground at 0. It must be the other one, 4u sine theta on g. Okay, so I now know that. Where did it hit the ground then? Because that's what I want to know. Sub that into our expression for horizontal displacements. 2u times 4u sine theta on g times cos theta. Playing around with that, I just pulled it together into a double angle. So I've got 4u squared sine 2 theta on g. At least I now know what the maximum range is. I need to know that, because remember we were trying to prove it was, what was the percentage? It was, hang on, let's go back. There it is. I want to show it's less than 37% of the maximum range. So I found the range. Maximum range, 4u squared on, how do I know that? Well, it's a trig function. Maximum of that trig function is 4u squared on g. It also explains why maximum range is 45 degrees if you think about it. Because sine 2 theta is 1, when sine a maximum, at 90 degrees, 2 theta is 90, 45 degrees. What about our target? Where's that going to be? So d plus ut, we end up with d plus 4u squared sine theta on g. Now I want the projectile to hit the target, therefore at the time it hits the ground, that target can't have gone further than where it hits, because then I've got no chance of hitting it if it's already gone past that point. So if that's the case, what I'm saying is I would like the displacement to be less than the displacement of the projectile, because then at least it's got a chance of hitting it. In other words, that's what I'm now trying to do. D plus 4u squared sine theta on g is less than or equal to 4u sine 2 theta on g. D has to be less than or equal to that amount there. Now, that expression on the right hand side, because 4u squared on g, remember these are all constant, the only thing we could change was theta. So that's going to be maximised when sine 2 theta minus sine theta is maximised. Let's use a bit of calculus then. I don't care about the other letters, I'm just looking at that expression. Its derivative, I know it's going to be maximised when the derivative is equal to 0. There's the derivative, stationary points if you like. Okay, I now know cos theta. I know it's plus square root of 33 because I'm firing it at an acute angle. Okay, I can now get cos theta down to being that lovely expression. It's about 0.8431. I'm actually more interested in sine theta. I need that as well, because if you look at what I'm substituting into, that turns out to be 0.5378. So D is less than or equal to that. And if you work that calculation out, it's 0.3690, approximately 0.37. So yeah, D must be 37% of the maximum range. So that's what we basically just found. 23 then, let's have a look at that one. This time they're projecting 2 projectiles, one from the origin, but one up higher at H. But the one up high has been projected horizontally, just starts off horizontally. They gave us the 2 position vectors of the 2 different particles there. Theta is chosen so that tan theta is 2, and we know they do collide. We know that. First part of the question, showing cos theta is 1 on root 5, just verify V is root 5u. Well, remember tan theta is 2. There we go. That was nice. 1 on root 5, there we go. But if I substitute that in, well, hang on, they collide, remember? That means their horizontal and their vertical displacements are equal. I'm using the vertical displacements because if I substitute in cos theta for that, we get V equals root 5u. Okay, I suppose that's why they might have given us that hint there, because by giving us cos theta, that sort of suggests you're going to use the horizontal component, because that's the one that had cos theta in it. The vertical one had sine theta. But now we want to show they collide at this particular time. So now I'll use the vertical components. They've got to be equal as well. Substituting in, okay, we just got to make t the subject of all this. Oh, sine theta. Well, we can work out sine theta from our triangle as well. That's going to be 2 on root 5. And, okay, it comes out. There it is. T equals h on 2u. When the particles collide, their velocity vectors are perpendicular. Now we're going to show this, that h is 2u squared on g. Well, let's find those two velocity vectors. There's the one for A, there's the one for B. They're perpendicular, so their dot product must be 0. Okay, there's the dot product. We're saying that is equal to 0. Whew, okay. Show that h equals this, is what we're attempting to do. Well, let me just go back a bit. Somehow I've got to get h into this expression. I've got values for cos theta and sine theta, that's fine. There is no t in there, but we also, hang on, let's just go back a bit. There we go. We've got an expression for t that has h, so that's how we can get h into our problem. Subbing all that in, bit of manipulation to get there, but we've got this quadratic here. And it is a quadratic in terms of, well, I could think of it in terms of u, I could think of it in terms of t, but actually it's a perfect square. If you look at it, that is a perfect square. So t is u on g. We know that. Now what are we trying to show again? H is 2u squared on g. So t is u on g, but that means, because remember we said t was h on 2u. That means h on 2u is u on g. That came from part B. Brilliant. Just comes out nicely then. Prior to the collision, the trajectory of particle A was a parabola. Well, it's always a parabola. I guess what they're saying is once it hits, it's no longer going to be a parabola because some other force has now been applied to it. It'll go off again. It'll be a new parabola maybe, but it won't be the same parabola. Find the height of the vertex of the parabola above the horizontal plane, and the answer's in terms of h. Okay, what do we know? Maximum height, that will occur when vertical velocity is equal to 0. Sub in. So I now know the time it happens. We want to find the height. But hang on. 2u on g, that would be the same as h on u, because of what we found u was. Sub that in to find where it happens. And there it is in terms of h. Whew. Okay. 10A.